Forces. A force is a push or pull, something that changes the motion of an object. Gravity is the force that objects exert on each other because of their masses. Friction is a force that resists the motion between two surfaces in contact. History. In the mid 1600s, English scientist Sir Isaac Newton studied the effects of forces on objects. He formulated three laws of motion that are still helping people describe and predict the motions of objects today. Newton's ideas were built on those of other scientists, in particular the Italian scientist Galileo Galilei. These are a couple of video clips that I'm getting ready to show you about Galileo and Newton, their background, their history.
Galileo Galilei was a mathematician, physicist, philosopher, and astronomer. He is often considered the father of modern science.
Galileo was the one who really put together the principles of experiment, theory, and mathematics together into a common framework.
Probably more than anyone else, Galileo was really the person responsible for developing modern astronomy.
Galileo was born in Pisa, Italy in 1564. He was educated in a Jesuit monastery before he studied medicine at the University of Pisa. Galileo first gained fame when he discovered what is now called the law of the pendulum.
One day in the cathedral, he was watching the lamps that were hanging from the ceiling and saw them swaying back and forth, and started thinking about the nature of a pendulum.
He found that the amplitude of the swing doesn't matter, but the length of the pendulum does. And this became the genesis of regulation of clocks, for which he became instantly famous.
Galileo also gained fame by supposedly using the Leaning Tower of Pisa to prove the law of constant acceleration.
It's said that Galileo dropped two steel balls of different masses but the same material from the Leaning Tower of Pisa, and they landed at the same time, in contrast to what Aristotle would have predicted.
What's important about this is not only the result, but the fact that he ushered in this new method of doing science, where you conduct an experiment to test a hypothesis. He showed that you have to do more than just think something's true, you have to prove it.
In 1609, Galileo heard about a telescope built by a Dutch eyeglass maker. He soon built his own, 32 times more powerful, and started studying the heavens.
When Galileo looked at Jupiter through a telescope, he discovered four tiny little lights that seemed to circle Jupiter. Those are what are now referred to as the Galilean moons.
This confirmed Copernicus's idea that celestial bodies rotate each other. He also looked at Venus and found that it had phases.
This discovery was revolutionary because it really proved beyond the shadow of a doubt that the Earth is not the center of the universe.
During his life, Galileo published his findings in several manuscripts. Most of these earned him the ire of the Catholic Church, which eventually labeled him a heretic. He was sentenced to house arrest for the last years of his life and died on January 8, 1642.
Galileo was really the father of Western science. Prior to his time, there really was not the same sensibility of experimental science. Galileo is fundamentally responsible for what we know about the universe today.
In 1687, the Principia was published. Acknowledging his love of ancient Greek thought, the book was structured as a classical treatise in rhetorical argument and logic. The mathematical reasoning was largely in Euclidean geometry, the geometry of the ancient Greeks. The book opened with definitions of mass, types of forces, and inertia, each presented in a radically new light. Using these definitions, he postulated three laws of motion. On these three laws, Newton constructed his framework for dynamics and celestial mechanics, the bases of modern science. Using his laws of gravitation and measurable data, he described the structure of the universe. He showed how to find masses of planets, why the Earth is flat at the poles, and why there is a bulge at the equator, how the tides work, the precession of the equinoxes, and the motion of comets.
Newton's Principia is generally reckoned to be the single most important scientific book ever written and published. People attribute this singular importance to the Principia because for the first time it set forth a working, quantitative, exact, mathematical system based upon experiment and critical observation. I know of no other work which had so profound an effect upon the very nature of science itself.
The following are Sir Isaac Newton's 3 laws of motion. The first law, aka or also known as the law of inertia, meaning objects at rest remain at rest and objects in motion remain in motion with the same velocity, so the same speed and direction, unless acted upon by an unbalanced force. There are several examples that I have included. However, on your notes packet, you need to choose just one and write it on the lines provided. And you will do that for all 3 laws, the first, second, and third law. You will choose one of the examples that I have provided for you and write that on the lines. Examples of first law of motion include blood rushing from your head to your feet while quickly stopping when riding on a descending elevator. The head of a hammer can be tightened onto the wooden handle by banging the bottom of the handle hard against a surface. To dislodge ketchup from the bottom of a ketchup bottle, it is often turned upside down and thrusted downward at high speeds and then abruptly halted. Headrests are placed in cars to prevent whiplash injuries during rear-end collisions. While riding a skateboard or a wagon or bicycle, you fly forward off the board when hitting a curb or a rock or other object that abruptly halts the motion of the skateboard. Inertia is the resistance of an object to change in the speed or the direction of its motion. Newton's second law is the acceleration of an object increases with increased force and decreases with increased mass. The direction in which an object accelerated is the same as the direction of the force. Examples: when you throw 2 stones of different masses at the same speed, the lighter one will move the fastest. And there's a mathematical equation that goes along with Newton's second law, F equals ma. F stands for the force, the net force, m stands for mass, and a stands for acceleration. The unit for force is Newton, a capital N. Centripetal force is any force that keeps an object moving in a circle. Force points toward the center of the circle. Without the centripetal force, the objects would go flying off in a straight line. And as you can see, you've got a couple of diagrams, and I'm sure many of you have ridden on a roller coaster before. Newton's third law is every time one object exerts a force on another object, the second object exerts a force that is equal in size and opposite in direction back on the first object, aka action-reaction pairs. You'll hear those terms used a lot when referred to the third law of motion. The 3 laws are not independent of one another, meaning they do not act alone. They are used together to explain the motion of objects. Examples of the third law include a variety of action-reaction pairs, force pairs are evident in nature. Consider the propulsion of a fish through the water. A fish uses its fins to push water backwards, but a push on the water will only serve to accelerate the water. Since forces result from mutual interactions, the water must also be pushing the fish forward, propelling the fish through the water. The size of the force on the water equals the size of the force on the fish. The direction of the force on the water, which is backwards, is the opposite the direction of the force on the fish, which is forward. For every action, there is an equal in size and opposite in direction reaction force. An action-reaction force pair make it possible for the fish to swim. Consider the flying motion of a bird. A bird flies by using its wings. The wings of a bird push air downwards. Since forces result from the mutual interactions, the air must also be pushing the bird upwards. The size of the force on the air equals the size of the force on the bird. The direction of the force on the air, which is downwards, is opposite the direction of the force on the bird, which is upwards. For every action, there is an equal in size and opposite in direction reaction. Action-reaction force pairs make it possible for birds to fly. Consider the motion of a car on the way to school. A car is equipped with wheels that spin. As the wheels spin, they grip the road and push the road backwards. Since forces result from mutual interactions, the road must also be pushing the wheels forward. The size of the force on the road equals the size of the force on the wheels, or car. The direction of the force on the road, which is backwards, is opposite the direction of the force on the wheels, which is forward. For every action, there is an equal in size and opposite in direction reaction. Action-reaction force pairs make it possible for cars to move along a roadway surface. Momentum is a measure of mass in motion. The momentum of an object is the product of its mass and its velocity. The equation for momentum is P equals mv, with P meaning momentum, m meaning mass, v meaning velocity. The standard unit for momentum is kilograms times meters per second. Gravity is acceleration due to Earth's gravity, which is represented with a lowercase g, is equal to 9.8 meters per second squared at Earth's surface. You calculate the force due to gravity on a mass close to the Earth's surface with the equation F equals mg, with F standing for force, m standing for mass, and g standing for the gravity, acceleration of gravity. Gravity and friction. Mass is a measure of how much matter an object contains. Weight is the force of gravity on an object. Mass is a property that an object has no matter where it is located. Weight depends on the force of gravity acting on that object. So, would a book weigh the same on Earth as it does on the moon? No, it wouldn't, because the gravitational force is different. However, would that book still have the same mass on Earth as it does on the moon? Yes, because the matter has not changed as far as how much it takes up, how much matter it contains. How much frictional force depends on the type of the surface. For examples would be wood, ice, carpet, cement are types of surfaces. There would be more frictional force on carpet than there would be on ice. Friction causes heat. As the individual molecules in an object move faster, the temperature of the object increases. Example of friction would be rubbing your hands together. Whenever it's cold outside and you're rubbing your hands together, you're trying to make them heat up. Well, that friction between your two hands sliding together is causing heat. Pressure is a measure of how much force is acting on a certain area. We've talked about pressure before in our weather unit. High and low pressure, how much air molecules are pushing down on an area. The equation for pressure is pressure equals force divided by area, or P equals F over A. The standard unit for pressure is Pascal, or PA. A Pascal is the same as a Newton divided by or over meters squared.